Good morning, ladies and gentlemen. Today we're going to discuss matched pairs T intervals. But first, a quick word from our sponsor. Couch Potato Brand would like you to try their new peanut flavored snacks. Are you allergic to peanuts? Don't worry, as the snacks are flavored with the 100% fake peanut product Beyond Peanuts. You can almost not tell the difference. Almost. All right, ladies and gentlemen, that's the sponsored word. I'm intrigued, I'll tell you that much. Okay, so I'm going to do the problem that was assigned for homework yesterday, page 507, number 20. So if you don't remember, just take a moment and read through that problem. It's the problem with the tuition. Okay, so part A says to create a 90% confidence interval, and of course I wrote 95, but anyway, it's 90% confidence interval, and it says to be sure to justify the procedure. Now, I wanted to go through all four stages here because I've noticed some of you are sort of, anytime there's a confidence interval problem, you're kind of like skipping the justify stage and the summary stage, and even sometimes the plan stage. You're just kind of going right into the showing the work. But I need you to understand that this is also an inference procedure, just like a hypothesis test. They accomplish different goals, but you still need to justify that you can use a certain distribution because we are still sampling, right? We're making an inference on the population based on a sample. So it is necessary to go through all four of these stages. Anyway, I've written a lot of it down already. So of course, you can adjust the speed at which you watch the video. And so anyway, let's get into it. So we're going to do a 90% confidence level, as we were told. This will be a matched pairs T interval. How do I know that? Well, reading through it, notice that, yeah, there are two lists of numbers, but each of those lists is being generated from the same sample of 19 public colleges and universities. So this one sample of, in this case, universities and colleges is generating both lists of data. And so we have a very natural way of pairing each resident and non-resident number. All right, so this is going to be a matched pairs T interval. And my parameter of interest will be mu of D. This is the true average difference between resident and non-resident tuition. And I'm going to do it in the order of res versus non-res. Okay. All right, let's now justify. Again, this is the step a lot of us are sort of skipping. So it is mentioned that a random sample of schools was selected. So random/representative sample, good to go. These 19 schools is going to be less than 10% of the colleges and universities for sure. The nearly normal condition, we're going to check that in a moment. And remember, when we're doing a matched pairs procedure, we have to sort of make it clear how we're pairing the data. And it's very clear that we should pair this data by school. And again, I'm doing my subtraction in the order of residential versus non-residential. All right, the nearly normal condition. Now, let's go to our calculator. In my calculator, I've already input list one with the residential prices and list two with my non-residential prices. But remember, in a matched pairs test, I'm not actually interested in the values of list one or the values of list two. I'm actually interested in the difference between these values. Okay, so how much more are non-residential people paying? That's essentially what we're kind of trying to scope out here. So again, I'm going to do res versus non-res. So for me, that's list one minus list two. And so notice I'm highlighting list three, and I'm going to just press second L1 minus second L2, enter. And now I have a list of all the differences, residential versus non-residential. And as far as I know, as far as I care about, list three is the data. list 1 and list 2 at this point, I'm going to completely ignore and forget about. All I care about is that there was a difference of $4,700 here, a difference of $3,700 here, so on and so forth. Now my question, the question is, what are my sample statistics and everything like that, so that I can build my confidence interval. But again, remember, we're still testing the nearly normal condition, so I'm going to take that list 3, the list of differences, and I'm going to put it into a normal probability plot to see if it's nearly linear. So there we have it. Normal probability plot is, remember this last icon, my data of interest is in list 3. And zoom 9 will get me there. And there you have it. That's pretty nicely linear. And so, of course, to finish off this condition, we can say that the normal probability plot of differences is nearly linear. Therefore, distribution, or the sample, let's say the sample's distribution of differences is, not in, is nearly normal. Okay, there we have it. So all 4 conditions are met, and the fact that these 4 conditions are met means that in general, my sample mean differences will be distributed using the t-distribution centered at mu of d, which is really what I'm trying to gauge with building this confidence interval. Notice I'm not making any assumptions about mu of d. So mu of d is just going to stay as mu of d for this confidence interval procedure. We are going to have to approximate sigma d over radical n. N is 19. And to approximate sigma, I'm going to use the sample standard deviation. So let's go ahead and get that. So I'm going to go to stat, calc 1 variable stats. And in this case, I want list 3. We'll calculate. So my average difference is, my average for the sample at least, is negative $4,315.79. Let's write that down. Negative 4315. All right, so X bar D is equal to negative 4315 point. I'm just going to say 0.79. These are in dollars. And the standard deviation of differences is 1,373.67. 1,373.67. Notice that even though the mean is negative, the standard deviation is positive. Remember, standard deviation is a measure of distance, so it will always be a positive number. Okay, so this means, all right, so again, remember, I approximate this using the sample standard deviation over, in this case, it can be radical 19. And so let's get that number. One 373.67 divided by square root of 19. Okay, and so the sampling distributions as standard error is 315.1415. 315.1415. Okay. Now to build the confidence interval, remember the confidence interval is always take your sample mean or your sample statistic, whatever you're interested in. In this case, it's mean, and add and subtract the margin of error. So in this case, our X bar D is negative 4,315.79 plus or minus. All right, T star. So I'm going to either use the T table or I'm going to use, my calculator has it, so I'm just going to use inverse T. So I will press second distribution, and I'm going to scroll down to inverse T. Since this is a 90% confidence interval, the area to the left is going to actually be 95. And my degrees of freedom, I believe, were 18, because remember my sample size was 19. Okay, so T star is 1.7341. Standard error, we just calculated it to be 315.1415. Okay, and I'm gonna go ahead and calculate this. I'm just gonna pause. You don't need to see me type the information in, so hold on. All right, welcome back. And after calculating the confidence interval, we get negative $4,862 to negative $3,769. Okay. And I'm just going to show you how to do this also on your calculator. I already did it just to actually check my work, but you can do this all on your calculator, and then we'll get to the interpretation of that confidence interval. But if you just go to stat, scroll over to tests. Now, remember, like I said yesterday, these matched pair procedures are just like the one sample T procedures, because we're really just studying one list of data. In this case, we want a T interval. Okay, once you scroll down there, we could either enter the data or the stats. Our data is in list 3, and so I'm just going to use that. But if I did not have the data and I just had the statistics, then I'd plug those statistics in. In other words, if I was just given my X bar value and my standard deviation, sample standard deviation, and my sample size, right? But in this case, like I said, we have the data, so I'm going to use the data. I'm going to tell the calculator to read list 3. My confidence level is 0.9, right? And notice that's different from the number that I entered into inverse T, because that inverse T is the percentile of like the upper bound of the rejection, of the upper rejection region. All right, so confidence level 90, enter. And then here you got your T interval. And notice that it also, if you just enter the list of data, it'll also give you your sample statistics as well. All right, so there we have it. That's our confidence interval. Now to summarize, what this means is that we are, this is a 90% confidence interval. We are 90% confident that the true mean difference in tuition, residential minus non-residential, is between the negative $4,862 and negative $3,769. Okay, and there you have it. That is that's parts A and B. Part C now is actually kind of interesting. It says that a national magazine claims that the public institutions charge state residents an average of $4,000 less for tuition each semester. What does your confidence interval indicate about the validity of this assertion? Well, the fact that negative 4,000 exists in this interval means that that assertion is completely feasible. And so what we would say is, well, yeah, it's possible. We don't have evidence really to reject that claim. In fact, this confidence interval that we just built, so I've been trying to sort of get you to see this relationship between confidence intervals and two-tailed tests. So if I were to take the same exact data and test the following hypotheses, that mu of D was negative $4,000, and then the alternative, that mu of D was not equal to negative $4,000, we would end up failing to reject H null. So the hypothesis test that I've just written here and this confidence interval should always, these results should always agree with one another as long as we have an alpha level, in this case of 0.1. So I need my alpha plus my confidence level to equal 1. And I have to be running a two-tailed test. And if that's the case, then this hypothesis test and this confidence interval will always agree with one another. And when I say they'll always agree with one another, basically in this situation, notice that this confidence interval includes negative 4,000. So when we run this hypothesis test, we would not be able to reject that null hypothesis. It is feasible, in fact, that mu of D is equal to negative 4,000. And if you don't believe me, you can go ahead and just run the hypothesis, this exact hypothesis test on your calculator. We've already checked the conditions. Notice that these conditions would be the same regardless of whether we're running a hypothesis test or a confidence interval, right? The assumption that mu of D is equal to negative 4,000 does not come into play into any of these justifications. And so therefore, one thing that's nice about when we're dealing with means is the justification for intervals and hypothesis tests are identical. So that's kind of nice. But anyway, check for yourself, see that if you run this hypothesis test, you will end up failing to reject H null at an alpha level of 0.1. And that should make sense because the confidence interval, the 90% confidence interval, and a hypothesis test of alpha at alpha equals 0.1, they will always agree with one another. Again, it has to be a two-tailed test. All right. I think I'm going to actually do a completely separate video with this concept. But anyway, I'm rambling at this point. So, ladies and gentlemen, I hope you enjoyed that video, and I will talk to you soon. Please feel free to ask any questions at any time. All right, bye.